So, hello everyone. It's been a while since I've recorded these videos because I was unsure if I was to proceed with this, but I've decided that I've found another nice video that I would want to share with you. So, this problem might not look completely related to right triangles, but it actually is because we're going to also put auxiliary lines and dilate the figure a little, and it's going to form a right triangle, which is going to be really important to completing this problem today. So as you can see, we have a right trapezoid, ABCD, and AB is equal to BC. Whoops. AD is equal to half of AB or BC. So we know that there is a point P inside of this trapezoid, so that AP equals 1, BP equals 2, and CP equals 3. So, in order to find out the area of the trapezoid ABCD, we must have to know at least one between AB, BC, and AD, because then we will know the two bases and the height, which is going to enable us to figure out the area. So, our solution, there is a special rotation we have to make to this figure in order to solve this problem. So it has something to do with AB equals BC, and I can let you think about it for a moment. So now that probably some of you have thought about it, we're going to add in two auxiliary lines that are going to be really important to solving this problem. So we know that the angle ABC is 90 degrees because ABCD is a right trapezoid. So what if we rotated the triangle ABP 90 degrees in this direction? Whoops. Then we would get a shape. This is annoying. Then we would get the shape PBP will be rotated to this point, which we're going to call, let me see, and we also know the OneNote drawing technology is sometimes really bad when you have to draw shapes. But yeah, we'll go with this, and I'll fix it later. So, as you can see, I've rotated the triangle ABP over a little. I'll just change this a little bit so that it fits up with here. Here we go. So as you can see, we rotated this triangle ABP so that it now is the triangle BC, and we'll name this point, we can name this point O. So now we have changed this triangle ABP into the triangle BCO, and we can prove that they are indeed congruent because AB equals BC, and we know that this angle equals 90 degrees, and we have formed these two angles. So, let me write. We have rotated the triangle ABP to 90 degrees to form the triangle BCO. So now we have this triangle BCO. There's something neat that we can do here, which is you might have figured out that the angle PBO is also 90 degrees because it's equal to the angle ABC. This is a property of rotation because since AB is perpendicular to BC, PB will also be perpendicular to BO. So if we connect the lines, the points P and O, OneNote drawing technology, the lines, it's not always lined up as it looks, but this will work even though it isn't really neat. We've lined this up, so now we have PO is connected. So now we know that the angle PBO is equal to 90 degrees, and since BP and BO are the two corresponding sides of two similar triangles, which are BCO and ABP, we know BP equals BO equals 2. And we can apply the Pythagorean theorem here to figure out the length of OP. So we know that OP equals the square root. Let me insert this equation, symbols. Where is the square root symbol? Here it is, the square root symbol is the square root of BP. We'll put a little subscript. Where is the subscript? BP squared. Yes, so we have subscript BP, let's see if this works, plus BO squared. Oh, that's uppercase O. So let's close this. We'll do this. Now it should end the formula. Nope, it's not working. So let me try this again. Yeah, now it works. So we have that OP equals the square root. Oh, I have to do the equation thing all over again. But the square root of, or 2 times the square root of 2. Since 2 squared plus 2 squared is 8, the square root of 8 can also be written as 2 times the square root of 2. I might need to tinker around with this a little bit. Yeah, it isn't working. So we know this, and we can also devise an important fact from this. Since we also know, it's not working. Since we also know that CO equals 1 and CP equals 3, we have a coincidence, or it might not be a coincidence, that CO squared plus PO squared equals PC squared, since the square root of 8 squared plus 1 squared equals 3 squared, which is 9. So we know that the angle POC is equal to 90 degrees. So what use is this? We must not, there is an important fact here. Because BP is equal to BO, the triangle BPO is a right isosceles triangle, and the angles BPO and BOP are both equal to 45 degrees. What is kind of fun about this is that we know that, because we can devise that the angle BOC is equal to 45 plus 90 equals 135 degrees. What is important about this? We have shown that the angle APB is also equal to the angle BOC, so that we can also devise that the angle APB is equal to 135 degrees, thereby making the points A, P, and O on one straight line. This is a very important fact, that APO are on one straight line. So now we have an important fact here, because we can use this fact to drop another perpendicular. So the perpendicular we're going to drop is going to be, we're going to drop another perpendicular inside of the triangle BPO. So we're going to add a line starting from B. I don't know why they did this OneNote drawing technology. it's very bad. You have to do it a lot of times in order for it to work. See? But if we could connect. Still not letting me do this. If we can connect, we'll do this. We're going to do this. So let me see. So let's say, oh, one note, come on. Let's connect this up, and let's move this a little, so that it's directly perpendicular to, I know this doesn't look very perpendicular, but it's the best we have. I'm going to connect this up. We're going to find the point E. Whoops. Yeah, I can do it about here. We can find the point E. I need to make this bigger. So that we know, let's see, drop a perpendicular BE onto the side PO of the isosceles right triangle BPO. So now you kind of know where I'm headed, because we know that PE equals PO. We know that PE equals PO. We know that PE equals PO. And since PE equals EO, and since PO equals 2 times the square root of 2, as we proved earlier, we know that PE equals EO, and they're both equal to the square root of 2. So you can see why I dropped this perpendicular order to figure out this, because we can devise AB now, which is going to be really important if we're going to figure out the area of this trapezoid. So we know, so we can apply the Pythagorean theorem again. Here we have BE AE equals 1 plus the square root of 2. We need a lot of these equations in here. Plus the square root of 2. Whoops, I have to put this in here. Since AP equals 1, as we're given, we know that, we also know that BE is equal, we can also apply a Pythagorean theorem here, so we know that BE is equal to BP squared, which is 4, minus the square root of 2, which is also the square root of 2. So now we can use these two lengths to figure out the length of AB. The length of AB is going to be the square root of 2 squared plus parentheses 1 plus the square root of 2 squared. So I calculated this earlier. However, we don't actually have to find out the exact length of AB. If you think the area of the trapezoid is AB times parentheses AD plus BC. So and since AD is 1/2 of AB, we get the area is 1/2 times AB times 1/2. 1/2 AB times 1/2 times AB times 1/2 3/2 of AB, since AD plus BC is 3/2 of AB. So we don't actually even have to figure out AB itself. We only have to know AB squared. AB squared is thereby 5 plus 2 square root of 2. I calculated this earlier, so because it's kind of hard to calculate. It takes a little while, so I've calculated this earlier. It's 5 plus 2 square root of 2. Now we can figure out the area of ABCD. As we said earlier, the area A equals AB squared. I'll just do this because I'm too lazy to bother. AB squared times 3 over 2 times AB squared times, whoops, it's AB times 3 over 2, my bad, times 1/2, which is equal to 3/4 times AB squared. So we can multiply 5 plus 2 square root of 2. It's hard to input these. 5 plus 2 square root of 2, equations, times 3 over 4. So the area is equal. Or now we have 4. Let me see if we can do fractions here. It's solely to make this look better. Let me see, A over B. Where are the templates for this? We're going to make the two A over B constants. Okay, so we have, well, let me find a good symbol. Never mind. So, or we can also have, I don't really need these. 15 plus 6 square root of 2. Again, I have to use equations again. 6 square root of 2. And then the whole thing divided by 4. Or we can put this over. I mean, I could do this fancy way of doing this, but it doesn't really work out very well. I could always do this. Technically, it looks something like this if you were to write it out yourself. So I could put this up here. Yeah. Let me refine this a little bit. So now we know this area. So I'm going to refine it a little so that it looks better. I might underline this text because I'm not very good with OneNote, things in OneNote and all the equations and everything. So yeah, this will look like the answer you can get if you wrote it out on paper. So now we have the area of the trapezoid ABCD, which is what we wanted to figure out. So recap about this problem. It might seem very confusing at first if you see all these auxiliary lines that I added, but it's just dropping perpendiculars and putting in the Pythagorean theorem numerous times. When you see these problems where you have 3 technically unrelated lengths, you might want to translate them into a position where it would be easier to develop relations between these. And you can also use number theory and think of what the relationship between 1, 2, and 3 is. You might think of something along the lines about 3 squared minus 1 squared is 2 times square root of 2, which is going to be pretty important. So this is going to be today's problem of the day, and we're also going to be doing a special talk on ellipses today. So see you guys in a few days.